Hello, happy week 6. So let's go ahead and get going into this. We don't got a lot of time left, y'all. We are basically done. We have this week and next week. That's it, and then we're done. I mean, we have a third week after that, but that's gonna be a makeup week. So stay on it. Two more weeks of lessons. You're almost there. So close. All right. So this week we are starting off on page 38. So 38 is talking about properties of limits. Last week we explored how to look at limits using graphs and tables and using your graphing calculator to find the answers. And that's great and that's cool, but we also need to learn how to find them algebraically so that we're not always looking at a graph to do it. So with that, you can use your skills from last week to help check your answers this week. But this week, I do want to see you show the work on the homework assignment. So you want to make sure that you're working things out as you're going so that you can see how it solves algebraically so that you're not depending on the tables and the graphs for everything. This first part's kind of silly. Not silly, but just kind of a repeat of it's not something I'm going to necessarily sit and explain to you, but I'll put them up in just a second. The properties, there's a few of them, so you just probably going to want to pause it and copy them down as you get to that. So what happens is if k and c are real integers, where k is going to be like, sorry, I had to look at my notes. K is going to be like something that is being multiplied or being a scalar factor in our limits. If k and c are real numbers, though, c being the number that we are approaching with our limit, and n is a positive integer, which will happen in your exponents. You'll see kind of as you get down. These don't always apply. And the limit of f of x as x is approaching c, and the limit as x is approaching c of g of x both exist, then a couple rules happen. The first one is that scalar multiple I was saying, is that you could take a scalar multiple and factor it out. So the limit as x is approaching c of a function multiplied by k is the same thing as the limit as x is approaching c of the function, then multiplying by k at the end. The sum and difference property is that if you have a limit as x is approaching c, and that's an f there, I know it's kind of hard to see, of f of x plus or minus g of x, you can separate that into two separate limits and do the limit as x approaches c of f of x plus or minus the limit as x approaching c of g of x. You can do those as two separate limits. The product rule is very similar. If you have a product of f of x times g of x, you could separate them as two separate limits and then multiply the solutions at the end. Division, if you have the limit of a function divided by a function, you could separate that and do the limit of the first function, the limit of the second function, and then do a division problem. And the power and the nth root, if you have something raised to a power, you can do the limit first and then raise it to the power at the end. You'll get the same answer. Similarly, if you have a limit of something being nth rooted, cube rooted, square rooted, fourth rooted, fifth rooted, whatever, you can find the limit of the function inside and then take the root after. So again, pause that and copy those down. It's going to make more sense as we work through it. Now, the really important things that you got to make sure that you remember from here, and these are things that you want to kind of memorize in your head, is two very important limit rules. The first one is the limit, the constant limit. So the limit as x approaches, let's say as x approaches -1, of a constant 5. Well, the answer is 5. It will always be this. If the function is a constant value, then I don't care what x is approaching. The limit will always be that same constant. So I wrote that in general terms. The limit as x is approaching c of k, we don't care what c is. Because k is a constant number, -1, 5.6, 100. When it's a constant number, then the limit will be a constant number. The identity rule is that if you have a limit as x is approaching, let's use -1 again, of x. Well, because it's -1, it's going to be -1. So whenever this happens, whenever this is the identity, meaning that it's just x, if it's just x, then whatever c is approaching is what is going to be the answer, right? So if c is approaching, if x is approaching -1, whatever c is, whatever x is approaching, is the answer. So if x is approaching -1, the answer is -1. If x was approaching 5, the answer would be 5. If x was approaching 6.6, the answer would be 6.6. So whatever it's approaching is what the answer is going to be. That's all going to make a little bit more sense, like I said, as we do these examples. So I've got a few examples to look at. My first example is this. The limit as x is approaching 5 of 2x plus 1 over x squared minus 3. So I'm going to do some silliness here, and I want you to do it for these first couple ones. And on the homework, there's a couple they want you to do it for. But as you practice it and learn it, then you won't have to do this because you'll understand why we're doing it. So we're going to separate this by using our limit rules. The first thing I recognize is I could use the quotient rule, right? There is a function on the top and a function on the bottom. So I could separate this and say, okay, well, the limit as x is approaching 5 for the function 2x plus 1 divided by the limit as x is approaching 5 of the function on the bottom, x squared minus 3. Well, I could go even further here. Now I could say, great, I have a couple separate functions. In this top function, I could say, that's an addition problem. So I could separate it by using the sum and difference rules. Similarly, we could do the same thing on the bottom with the difference. That says difference, pretend it does. So up top, I could rewrite this as the limit as x is approaching 5 of 2x. Since there's a plus sign here, we'll put plus. The limit as x is approaching 5 of 1. And then on the bottom, we have the limit as x is approaching 5 of x squared. Since it's a minus sign, we'll put a minus sign here and then do the limit as x is approaching 5 of 3. Whew. Getting close, right? So we could still go further. Look at this top one. Right here, I've got a product rule. So I could separate that using the product rule. So in the top, I'm going to have the limit. Oh, sorry, it's not the product. It's a scalar factor, right? So right here, I could do a scalar factor. I could pull this 2 out. You could do it as a product as well, and you get the same answer, but I'm going to do it as a scalar because that's what I really wanted you to see. Scalar. All right, so it says because there's a constant in front of this x, I can pull the constant in front of the limit. So we'd have 2 times the limit as x is approaching 5 of x plus the limit as x is approaching 5 of 1. And on the bottom, we could use the power rule. The power rule, which says that I can just take this power, move it outside. So I can say the limit as x is approaching 5 of x, and then square it, minus the limit as x is approaching 5 of 3. So with this, a couple things happen. Now, those 2 rules that I said were super important. Like I said, I know that's a lot of writing the same thing and separating it. What we know then is because the ones I'm highlighting in blue, those apply the constant rule, right? The constant said that the limit as x approaches anything of a constant number is that constant number. So what I know then is that this is equal to 1, and this is equal to 3. So I know the limit here is plus 1 and plus 3. Over here, we can then look at this. These are both going to be the ones that I'm going to highlight here in green. These ones are identity rules. We said that the identity rule is that the limit as x approaches any value of c when it's just x as the function is equal to c. So in the top one, the limit as x is approaching 5. Well, as x is approaching 5 of x, it's 5. What we need to remember is there's that 2 out front then. So we're going to multiply 2 times that 5. Down here, I've got the limit as x is approaching 5 of x. So again, this is the identity function. So it's going to be 5 because that's what c is equal to. And then we square it. So then I can work this out. 2 times 5 is 10. 10 plus 1 is 11. And down here, 5 squared is 25. 25 plus, that's not supposed to be a plus, I'm sorry, minus. 25 minus 3 is 22. And that simplifies to 1/2. So some of you may be noticing something really, really important there. All I did was plug 5 in, right? When you look at what happened right here, compared with the original equation, it was just that 2 times 5 is 10 plus 1 is 11. 2 times 5 plus 1 is 11. Right here, I plug 5 in. 5 squared minus 3. 5 squared minus 3 is 22. So that does work. This is what we call a direct substitution. Let me scroll this down a little bit. So there is the problem if you want the nicer handwriting version of it. Let me get it to scroll down. There you go. Nicer handwriting. So long as a function is continuous, right? If it is continuous, or sometimes they like to say that the polynomial is a well-behaved polynomial, as long as that happens, you can use direct substitution, meaning that whatever the limit as x is approaching c of some sort of function is the f of c of that function. So in this case that we just did here, we said the limit as x is approaching 5 of our function, I'm not going to rewrite out the function, but of the function f of x, well, all it was is that we took 5 and plugged it in, so it was f of 5. Again, this only works, though, as long as the function is continuous. Now, what I mean by continuous, if you think about a parabola, that is a continuous function because there is a value for every single point that doesn't cause any confusion. For a linear graph, that is continuous because from negative infinity to infinity, there is a value for every single x that is concrete and makes sense. A function stops being continuous if, for example, it has a removable discontinuity. So a function like this would not be continuous because there is a removable discontinuity there. Piecewise functions that maybe do something like this, that would be not continuous because there is a jump discontinuity. Functions like the reciprocal functions that go up like this and have an asymptote here, that would have an infinite discontinuity, so it is not continuous. So whenever functions have holes or infinity lines or jump discontinuities, then we say they're not continuous and you can't use direct substitution. So as long as it's a well-behaved function, that's beautiful. You just plug it in and solve. Which kind of leads us to this being pretty nice and easy, right? This section is going to be super easy. It's just plug it in and test it. This leads us into the next section that isn't so easy. So I have another example just to kind of show you some more, kind of simplicities of this. Let me clear that. So the question says, for example, to determine if they can be solved, if a limit can be found with direct substitution. So direct sub, yes or no? And I have the question written out in just a second. So you may want to just watch me do this and then write it out in a second. So for example, I have two problems. The first one, the limit as x approaches -2 of the function 3x cubed plus 8x squared plus 11. Well, what we ask ourselves is, does that have any discontinuities? Is that function continuous? Is there a removable discontinuity or a hole like we called it? Is there an infinite discontinuity where the graph has some sort of asymptote that it trends toward? Is there a jump discontinuity where it suddenly jumps from one spot to a different spot? That function does not have that, right? If you kind of have a good idea of your functions, that's a cubic function. I know cubic functions are going to do some sort of shape like this, which is continuous, right? It trends up towards infinity, trends down towards negative infinity that way, but it is continuous. So I would say that yes, this is going to work, and we can test that. We can plug in -2 and see what happens. So 3 times -2 cubed plus 8 times -2 squared plus 11. Well, -2 cubed, -2 times -2 times -2, that is going to give us a negative number. 3 negatives stay negative. 2 times 2 times 2 is 8. Here I have my 8. -2 squared, well, negative times a negative is positive, so the negative goes away here, and 2 times 2 is 4, so it's a positive 4. And then plus 11. Here I multiply and I get -24. Here, 8, 16, 24, 32. And over here is 11. I add that together, and when I add that together, I get positive 9. So I would say that yes, the limit here can be found through direct substitution, and the limit as x approaching -2 of this function is 9. Now I did do a part B here so that we could see another type. In this one I said the limit as x is approaching 1 of x plus 5 over x squared minus 1. Well, when I look at this, the first thing that jumps out to me is this is a rational expression, meaning this denominator causes us to have a hole or a removable discontinuity, right? We know that our denominator cannot equal 0. So if I solve this, x squared cannot equal 1, which means x cannot equal plus or minus 1, right? If I plug in a positive 1 there, I get 1 minus 1, which is 0. If I plug in a negative 1 there, I get negative 1 squared, which is 1. 1 minus 1 is 0. So those two things cause us to have an issue. It causes our function to be discontinuous. I don't really like the way I'm saying that now. I would rather just say it's not continuous, right? Because this function is not continuous, it's got holes, it's got removable discontinuities, I would say that no, I can't use direct substitution to solve this, which ties into what we're going to talk about in the next page, on page, I don't even know what page I'm on right now. I think 38, 39, whatever. The next page, we're going to talk about how to worry about that then. So jumping us back over here, page 38. So on page 39, we're going to look at how to do that. So just putting this example back up. There it is. There's my answers. Go ahead and pause it, get that copied, and hopefully that helps with that first part. Like I said, the first page of notes should be super easy because you either just say it is solvable by direct substitution or it's not. Let me know if you have any questions. I'll be in my office hours all week. Bye!